Oh, hi. Okay, so this is 7.2 Introduction to pH. So in this section, define the term pH and explain the relationship between concentration of hydrogen and hydroxide ions in acids and bases. And 2, describe the proper way to use pH paper and pH meters and which should be used in a specific situation. Okay. So, importance of pH in biotechnology. Must maintain the pH of protein and DNA solutions, otherwise the molecules will denature and not function properly. That's important. Checking it often. In order to make buffers for biological molecules, it's important to understand pH, and you've done that a few times. And pH measures the number of hydrogen ions in solution. Okay, so properties of water as a solvent. So some of the water molecules break up into hydrogen and hydroxide ions when they're in solution. 1 times 10 to the negative 7 moles per liter hydrogen ions and 1 times 10 to the negative 7 moles per liter hydroxide ions would be in 1 liter of water. Water is therefore neutral and has a pH of 7, which is the negative log of hydrogen ion concentration. So no matter what the concentration of hydrogen and hydroxide ions are in a solution, that total amount will always add up to 10 to the negative 14. Acids and bases. As the concentration of hydrogen ions increases, the concentration of hydroxide ions decreases. An acid is a solution that has a pH of less than 7 and has more hydrogen ions than hydroxide ions in solution. A base is a solution that has a pH of more than 7 and has more hydroxide ions than hydrogen ions in solution. So a strong acid is a pH between 1 to 4. A weak acid is pH between 5 and 6. Neutral will be a pH of 7. Weak base is a pH between 8 to 10, and a strong base is a pH between 11 to 14. pH paper and pH meters. pH paper contains one or more chemical indicators on it, and then it changes colors depending on the amount of hydrogen ions in solution. So there's 2 types, and we don't use too much of these. If you do a science fair experiment, you might be able to use them more. But we have the wide range that are usually from 1 to 14. Sometimes they all look alike. You have to pick them out. Little containers we give you, little plastic containers. Just look carefully to see if that's the wide range. The narrow ranges can have it into the 0.5 pH values. Like for just acids, you can get ones that have just 1, 1.5, 2, 2.5, 3, then that would be it. You'd work out, first you do like the general one, get an idea, if you're pH of 6, but you really want to know if that's a pH of 6.5 or is it 6. So then you pull in the narrow range ones. Okay, then a pH meter, which we use, and I've got those ones that we've used for making buffers. It's an instrument that uses an electrode to detect the pH of a solution. So that's good for large numbers of samples that need to be tested and when you need to alter the pH. Of course, paper is just for one shot. You just want to pick up what that pH is right there at that time. Okay, so pH meter use, just if you got your book at home, you can use this too. It's fine. I know some people might have left their books at home. At school, I don't know, in your locker. So that's why it's good here. I'm just, any kind of content quiz I give you, it's going to be based on this slideshow. So let's start off by turning on the meter. So then you would rinse that with water. So we usually wash it first. Well, turn it on, check it out, then go ahead and, use distilled water to wash up underneath the electrode. And then place it in a pH 7 buffer standard. We should do that. If you're doing more accurate measurements, we should have that pH 7 buffer standard ready to go, and you put it in there. Now, while swirling the liquid, we use a spin bar there. Adjust the calibration knob until the display reads 7. So the real good pH electrode meter, you really want to get that going first. You want to set it at the pH 7 buffer standard, be able to maneuver or calibrate. Usually there's a CAL on the electrode. It'll indicate that you can set it at 7, matching up this buffer standard. And that's what you really want to do. Usually you get a little screwdriver and you can fix it on these older kinds of electrodes. Then rinse it again with distilled water, the electrode, and then place it in the solution that needs to be tested. Read the pH value. Hopefully you're okay. If you're using a strong acid, I would use a pH 4 buffer. I would calibrate it to that. If you're using a strong base, you would use a pH 10 buffer and adjust it accordingly. Okay, buffer standards are solutions that have a specific pH and are used to calibrate a pH meter. So sometimes it's necessary to alter the pH of a solution by adding an acid or bring down the pH or by adding a base to bring up the pH. And we usually do that, right, in class. So if we're going to bring down the pH, we use 1 molar hydrochloric acid in a little dropper bottle. If we're going to use it to bring it up, we're going to be using a little 1 molar sodium hydroxide. Okay, so those are pretty much the standard things I've been using with you to negotiate getting the right pH for your buffer. And you're going to see that later in 7.3. We'll talk about buffers. Okay, so review, if you, I would like you to do these questions in your notes, and that would be terrific. Now, I am going through a little bit more with pH, and let me just go ahead and see here what we've got. Okay, let's go back. We'll go back to buffers after this, but just to go over hydrogen hydroxide ion concentration, a little bit of math, a little bit of calculations I've put into this. I've been doing this now for about 3 or 4 years of just getting these word problems out there. I think it helps you too when you think about, you've worked with it in honors chemistry, or now you're doing AP Chem. These are not going to be the same, it's not as intense as AP Chem right now, but this is just to get it, just some basic relationships here. So I have this relationship here of Kw equals your concentration of hydrogen ions to hydroxide ions equals 1.00 times 10 to the negative 14th. So I have a couple of these problems in your notes section there that you need to calculate. So you do need your calculator that has a log function to do this. Not this one. This is just, now if you see hydrogen ion concentration as something that's an acid like hydrochloric acid, this is the hydrogen ion concentration, right? Because if it's acid, that's it. For here, this is a base. So you have to plug this value in where it says hydroxide ions concentration, put this guy in here, put it over this, and calculate hydrogen ion concentration that way. So obviously this is the answer to hydrogen ion concentration if it's an acid. If it's not an acid and you see a base, then plug it and then solve for hydrogen ion concentration. Okay, calculating pH part 1. pH measures the amount of hydrogen ions released by the acid when placed in a solution. So recall the link between dissociated acid-base strength in the previous lecture. Okay, when an acid is placed in solution, it releases hydrogen ions, and then these ions attach themselves to water molecules to make a hydronium ion. So you get H3O+. The more hydronium ions that are made, the more hydrogen ions that must be released, then you have the stronger acid. So this is hydrogen ions plus water, you get hydronium ions. Now, this means that to measure the pH of an acid, we are actually measuring the number of hydronium ions rather than the number of hydrogen ions, because hydrogen ions quickly form hydronium. So that's technically what's going on there. Calculating pH part 2, the formulating. The formula for calculating pH is pH equals the negative log of a hydronium ion concentration. So the square brackets around the hydronium ion means that you're using concentration of hydronium ions in the solution being measured. So the next step then would be figuring out how to use your calculator to solve problems using this logarithmic relationship. And I think we're all good there at this point. Each calculator will have its own order of button pushing to follow. So, you must learn to use your calculator. I'm sure you are okay with that. I can't imagine. Okay. Calculating pOH. The formula for pOH is pOH equals the negative log of hydroxide ions. So again, the squared brackets tell you the value within them is the concentration of the hydroxide ions in the solution being measured. Again, the calculator should be the toughest part of figuring out how to solve these problems. It's been a little sarcastic there, but I picked this up from somewhere else, but I'm sure you're fine with that. Okay. Now connecting pH to pOH. So pH measures the strength of an acid and pOH measures a base. So why then do we use pH to measure a base on the pH scale? Well, we convert pOH into pH because the relationship between the two values is shown here. pH plus pOH would equal 14. This means that if we're given this concentration of hydronium ions in an acid, we can find the pH and use that value to describe its strength. If we're given the concentration of hydroxide ions in a base, we can find the pOH and use the relationship above to convert the pOH into a pH value. So I have some of this stuff going on in the notes there. And you're just using calculation. I have equations right there. So if I'm doing this on a content quiz, the equations are going to be there. I'm not doing the memorization on this one. So again, here's an example of doing the pH for a specific concentration of hydronium ions, really hydrogen ions or hydronium ions. So then you would plug it in and then solve it, and then you got pH of 4.85. So again, people I think are pretty good with this. And then if you needed to get the hydrogen ions from a known pH, you would then flip it around and get it that way. I don't think I did those. That's the inverse log. And so if you're used to doing inverse log, you can do that, but I didn't put those in, I don't think now. Okay, let's go over buffers and buffer bonanza in the next slideshow. All right.